Swayam Prabha. Digital India. Educated India.
So the next section is going to be on narrowing down abnormal or normal section in the plant with negative selection algorithm based fault detection system. Okay, with that, over to you.
Now I start my presentation with this title: Narrowing down abnormal normal section in the plant with negative selection algorithm based fault detection system. In chemical plant monitoring system is requested for safe, stable, and efficient plant operation. The operator performs the recovery operation based on the information obtained by the system. However, if many alarms occur, there is a risk that responding to the malfunction will be late because operators cannot grasp which part of the plant is faulty. We built fault detection system using negative selection algorithm as a new method focusing on the relationship between process variables. First, consider the two-dimensional process variable space. When we plot all normal data into the space, we obtain self area and non-self area. Second, semi-randomly generate detector candidate in the space. If the candidate is out of normal area, candidate becomes a valid detector called non-self detector, which has a circular detection area. If the candidate is placed in the normal area, candidate will be eliminated because it is self-affinitive candidate. By repeat this procedure, we obtain the non-self detectors sufficiently covering non-self area. These non-self detectors can detect abnormality of two variables relationship. After that, current values are plotted into the variable space. If the plotted sample is out of non-self detectors, sample is just as normal. If the plotted sample is in the non-self detector, sample is judged as abnormal. This fault detection system using NSA cannot diagnose anomalies. There are two reasons for this. The one is that there is not enough information on monitoring results. It makes a binary judgment as to whether the data is in non-self detector or not. Therefore, it is difficult to know the possibility of anomaly of the monitoring data. Another is the method of variable selection is not suitable for diagnosis. Variables were selected for faster detection with fewer variable pairs. It is difficult to examine for where the anomaly occurred because it does not consider where the variable is located in the process. Objective of this study is the application of this fault detection system based on NSA to narrow down the abnormal and normal location in a plant. For more detailed monitoring results, we propose to evaluate how far the monitoring data is from the self and non-self area. First, generate self-detector using normal data which used to generate non-self detector. Next, find self-detector and non-self detector closest to the monitoring data, and calculate beta as the possibility of anomaly. Beta is calculated as the ratio of two values. One is the distance between the monitoring data and the nearest neighbor self-detector divided by the radius of the self-detector. And the other is the distance between the monitoring data and the nearest neighbor non-self-detector divided by the radius of the non-self-detector. The closer this value is to 1, the more likely it is to be abnormal. The closer it is to 0, the more likely it is to be normal. Our monitoring system is useful for monitoring abnormalities that bias measurement in control system. When sensor bias occurs, measurement of the control systems are more than the actual values. Then, MV changes in the direction of decreasing PV to make PV closer to SV. After that, PV returns to a value close to SV and the actual value decreases. The effect of changing actual value and MV is propagated to the process. Sensor bias is anomaly that cannot be noticed by monitoring the PV of the control system in one variable. The relationship between PV and MV of the control system will be monitored. In our detection system, we consider that it is possible to detect sensor bias from a breakdown in the relationship between the two variables by setting the PV on the horizontal axis and the MV on the vertical axis. Furthermore, when high possibility of anomaly is reported by a variable pair, determine if sensor bias is occurring by checking the direction of fluctuation of each variable. The direction of data fluctuation is expressed by a sign. If the variable is increasing from the steady state, the sign is plus. If it is decreasing, the sign is minus. If it remains steady state, the sign is 0. The figures below shows a detailed flow diagram of how the sign is judged. First, the monitoring data for the past 60 minutes is compared with the standard deviation of steady state operation data to check whether the condition is fluctuate or not. If it is fluctuate, the monitoring data is compared with the average value of the data over the past 60 minutes to check the direction of fluctuation. If sensor bias is occurring in the control system, the sign of the horizontal axis will be 0, and the sign of the vertical axis will be plus or minus. The set of sign of two variables is called as sign pattern. When sensor bias occurs, the sign pattern will be 0 plus or 0 minus. We propose a diagnostic flow to find the control system with sensor bias. First, calculate beta of the monitoring data. If the average of beta for the last 10 minutes is over 0.5, obtain the sign pattern of data. If the sign pattern is 0 plus or 0 minus, it is determined that a sensor bias occurs in the control system. After that, the beta at the time is presented as the possibility of sensor bias occurrence. Do this flow every minute. In this study, target process is a vinyl acetate monomer plant. The plant produces vinyl acetate monomer from oxygen, ethylene, and acetic acid. This is a schematic view of the vinyl acetate monomer plant. There are 26 control systems in this plant. We verified whether it is possible to narrow down the control systems that may cause sensor bias among these control systems. For the netting detector, we use data for 21,600 of operation with disturbance. 7 hours of data were monitored while the sensor bias was increased proportionally. We will show the monitoring result of three types of operation data when sensor bias occurs in PC130, FC550, and TC150. This table summarizes for each operating data the control systems that actually have sensor bias. Oh, sorry. This table summarizes for each operating data the control systems that actually have sensor bias, the number of variable pairs reporting high possibility of anomaly, the number of variable pairs determined to be sensor biased, and the control system that displayed the highest beta among the narrowed variable pairs. In the monitoring of malfunction 2 and 3, it was possible to narrow down from the variable pairs that reported a high possibility of anomaly to those that may be sensor biased. The narrowed variable pairs include a variable pair that monitors the actual control system with sensor bias, and the variable pair presented the highest beta. Correct narrowing down was done for malfunction 2 and 3. In the monitoring of malfunction 1, remaining variable pairs were not variable pairs. The remaining monitoring control systems that were not actually sensor biased. It means wrong narrowing down was done for malfunction 1. We will show the detailed monitoring result of malfunction 3 to explain why malfunction 2 and 3 got the correct results. These are monitoring results by variable pair, which is monitoring TC150, where the anomaly is actually occurring. The graph above shows the trend graph and the sign change of the variables on horizontal axis and the vertical axis. The bottom right figure shows the variable space with these two variables on the axis. TC150's PV isn't fluctuate, and TC150's MV is decreased. The graph below shows the change in beta. It exceeded 0.5 after 48 minutes from the occurrence of the anomaly. Since the beta is over 0.5 and the sign pattern is 0 minus, it can determine that a sensor bias is occurring in TC150. Next, we explain why malfunction 1 didn't get the correct results. These are the monitoring results by variable pair, which is monitoring PC130, where the anomaly is actually occurring. The graph above shows the trend graph and the sign change of the variables on horizontal axis and the vertical axis. The bottom right figure shows the variable space with these variables on the axis. PC130 PV is not fluctuate greatly, and PC130's MV is not fluctuate greatly. The graph below shows the change in beta. Beta is 0.5. Beta is over 0.5 momentarily, but it decreased thereafter. Since the sign pattern is 0, 0, it cannot determine that a sensor bias is occurring in PC130. We will explain why the MV did not fluctuate greatly. PC130 is a control system that controls the vaporizer pressure by adjusting the feed of ethylene. However, since the recycle flow rate is much larger than the newly added feed, Fi FI102F truly controls the PC130 measurements. It can be seen from the correlation coefficient. It was found that the sensor bias that occurs in a control system where the MV doesn't control the measurement cannot be diagnosed by the combination of variables proposed in this study. Conclusion. When sensor bias occurred in a control system where MV controlled PV certainly, it was possible to narrow down correctly by checking the direction of fluctuation of each variable. On the other hand, when sensor bias was occurring in a control system where MV was not controlling PV, we could not find a control system where sensor bias was actually occurring. It is expected that there are more such control systems in even larger chemical plants. Therefore, it is necessary to consider the methods that can diagnose sensor bias that occurs in such control systems. Thank you for your attention.
Thank you. Thank you for a nice talk. Questions? Okay, I had a quick question. So you were talking about the the negative selection algorithm. So in your case study, how big the plant is, because you're only detecting regions or sections of the plant. So how big is your case study? How many process variables are there in your case study?
I get operation data by visual modulator, so I don't think about actual plant.
Okay. So is this, if you are talking about detection in a section, so you should have fairly large number of variables or large number of sections, right? How many sections are there in your simulation?
So
Or maybe number of unit operations? How many unit operations?
I'm sorry.
Okay, that's fine. It is fine. Okay. Any other questions? So if not, we will thank the speaker. And thank you. Thank you so much.
Thank you.